Okay, let's get started. So for the final lecture, I wanted to talk a bit about vacuum decay. Luckily, actually, basically all the ingredients you need for this are things that you've already seen either in mine or Pratik's lecture, and we could have almost left as like some exercise for you to work through. So I'm going to be very schematic and just maybe point out things that are dangerous, places you may have got tripped up if you tried to do the calculation from scratch. As always, let's start with quantum mechanics, where we'll be able to get the key points, and then it just easily generalizes to quantum field theory. And to remind you of the simple case of tunneling between two degenerate minima, let me say I have a single degree of freedom, Q, which can either be at Q0 or Q1 are the two minima, and just normalize the potential so that V of Q01 is equal to 0. Then, as you know well from, say, WKB approximation, the rate of tunneling is parametrically given by to some numerical prefactor. Let me call it just A e to the minus some action. Let me say that this particle has mass of 1, just to avoid writing things out. Then the expression, is for the action is given by this. And this should immediately look familiar compared to our domain wall solution. In particular, the mass of our domain wall solutions had exactly the same form. We can, of course, also compute exactly the same thing using the path integral. So if we want to calculate as you know well, we can represent this transition amplitude in terms of a path integral. But just like in all of the other cases, this isn't particularly useful because there's no classical path that allows tunneling between, or allows the transition between Q0 and Q1. So instead what we do is analytically continue to Euclidean time. And then the object we need to consider is e to the minus h. Let me use curly t to represent Euclidean times. Q0, which is given by the Euclidean path integral q to the minus se. With the crucial sign change between the derivative term and the potential term. Well, maybe another useful thing to point out, just to connect with what follows, is that we can also write Q1 e to the minus h tau Q0, just as the sum over any energy eigenstates as And in this way, you can see that in the large Euclidean time limit, this right-hand side is going to be dominated by the value of n that has the smallest energy while still having some non-trivial overlap with the two vacua. And in this way, if we can evaluate this Euclidean path integral, we can also get some information about the energies of these vacua states. Okay, so hopefully this is nothing too surprising. And again, just like in many cases, you've seen these this week, we can evaluate this path integral in the semi-classical approximation. In particular, if we want to find the classical solution to the corresponding equations of motion, this is simply q double dot is equal to dv by dq, which looks exactly like the Newtonian equation of motion for a particle moving in an inverted potential. In this case, we have no friction, so we need some solution in which particle starts out at, say, q0 with this wave writing and transitions to reach q1. Then it's immediately obvious why the action of the associated tunneling, once we go back to real time, matches the form of the domain wall solution, because this was exactly the kind of calculation we did to calculate the domain wall mass. We have that Euclidean of this trajectory tau over 2 over 2 d tau, and now because we have some equivalent of the conserved energy, this is just 2v of q of tau. In particular, because we have that half Okay, so this instanton solution looks, again, of course, a lot like a domain wall solution, with now some non-trivial evolution in some finite part of imaginary time. Just to make sure, is all of this familiar? Has anyone got any questions of this so far? Okay, great. Then the next step is to, well, we don't just want the classical path, we want to evaluate the path integral, including also fluctuations around this classical path. And now here maybe comes the first subtlety, so we want to evaluate this path integral. This is e to the minus s Euclidean. So what this amounts to is I take my classical path, I look at small fluctuations delta q around this, and I do a path integral over these small fluctuations, but with the boundary conditions that at the starting point and the end point, the fluctuations vanish. Because the classical path, of course, solves the classical equations of motion, in the exponential I get no term that is linear in delta q, and this delta is some operator. and then plus higher order terms in the fluctuations that we can ignore. Now what you would naturally kind of write down here is this is just equal to e to the minus the action on the classical path over determinant of this operator delta, the power over half. But there are two subtleties here. The first complication is just like the domain wall solution, we have a zero mode here, and correspondingly we'll have an eigenfunction of this operator delta that has zero eigenvalue, making this 1 over determinant ill-defined. And maybe for later use it's worth pointing out that the associated eigenfunction, or the fluctuations, have the form of dq balanced by d tau. Just shifting our instanton in imaginary time, the energy of the instanton stays the same. Another useful thing to point out at this stage is that if you look at the associated eigenfunction, it has no nodes. So dq on this solution by dt simply starts here, it goes here. It's always increasing with imaginary time, so the corresponding eigenfunction never passes through zero. And then by some standard mathematical theories, that tells us that actually this zero eigenvalue is the smallest eigenvalue of the operator delta. In particular, this tells us that there's no negative eigenvalues, which would also cause a problem for the determinant operator, or the determinant of the operator. The other complication that you've already seen many times is that we've assumed that this tunneling process is dominated by a single instanton starting from here and going to here. But of course we can add together strings of different instantons. In this particular example, unlike the particle on the circle, if we tunnel from Q0 to Q1, then we can only then go back in the opposite direction. We can't continue going forwards. And when you do the summing of the various instantons, after a bit of work, you end up with Q1 e to the minus h tau, Q0 goes schematically as hyperbolic sinh. Some number k that I'll say just includes all of the stuff with the determinant, tau, then e to the minus s evaluated on this action. And a very similar calculation that you can check is that Q0 e to the minus h tau goes as cosh. And just as a sort of small sense check, you can see that in the large tau limit, if we wait sufficiently long, then information about the initial condition is completely lost. The chance of ending up in Q1 or in Q0 is equal. Okay, that was the warm-up. Any concerns so far? All happy? Good. Now we can efficiently move on to the decay of a metastable state in quantum mechanics. So let me now slightly tilt my potential so that the vacuum we start off in is not the perfectly stable vacuum. In particular, let me say there's some small energy difference between these two. Let me again call this Q0, this Q1. So maybe a first thing to think about is what we actually expect to get out for our answer. And it may well, or probably is familiar, but you might have forgotten that one of the ways we can think about decay of some state in quantum mechanics is the associated energy picking up an imaginary part. So if we say that we start off in, say, an energy eigenstate around Q0, then if we have an evolution with time, starting in this state, then you can immediately check that, well, you just immediately see that this is true. And if we pick up some imaginary part, as I say, we interpret this as the state decaying. Of course, in order to see this imaginary part of the energy, we're going to have to do something non-perturbative. If we look just at small fluctuations around Q0, we'll never be able to calculate it. So we have to make use of the path integral and a similar semi-classical analysis. So let me write that the partition function around Q0, not quite partition function, but let me consider the object Q0 e to the minus h tau again, Q0, just like before. This is still given by Q minus tau over 2 is equal to Q0. Likewise, Q tau over 2 is equal to Q0. No changes to before here. And again, exactly the same way as before, we still have that. I could save some writing here, but just to write it out again. Okay. And all of this tells me that I can extract the energy of the around the metastable vacuum exactly from this path integral, just with a factor of log and getting rid of the tau factor, which will turn up eventually. And once we cancel that out, will give us some decay rate rather than the total decay probability. Sorry. Q0. This part here. So here is, this part is coming from this overlap here. It's Q0 overlap with the lowest energy. Yeah, exactly. N is equal to 0. Yeah. In practice, this only gives us some prefactor. In the Q of t case, we'll see that actually by having some trace, this factor can go away, but here, to be careful, we should keep it. So now we need to know which trajectories can give sizable contributions to the right-hand side of this expression for Z0, so that in turn we can work out E0. The problem is exactly the same as we just did, except now, instead of a particle moving down some between two hills with equal heights, we want a trajectory where the particle starts from this vacuum, and because we want it to end up back in Q0, we need that the particle starts here, rolls along some trajectory to here, and then bounces back to the first trajectory, first hilltop. And this is what people usually call the bounce trajectory. So in particular, we want Q is equal to Q0, tau is equal to minus infinity, and that it returns to Q is equal to Q0, tau is equal to plus infinity. Exactly like this calculation up here, I can find such a trajectory and then I can carry out my path integral. One difference now is that when I combine multiple different bounces, say I start from Q0, bounce back to Q0, and then repeat this many times, I don't have to worry so much about the ordering of these different trajectories. This means that eventually what I get out is Z0 of tau is just summing over the bounces, multiple bounces, n towards the n over tutorial k to the n e to the minus. This is exactly just combining n different bounces, one after the other, to give the total expression for z. And this is equal to up to some prefactor, say proportional. Given by this expression. So now if I take this and I plug it into my expression for the energy, we get out that the shift in the energy around Q0 is, with some prefactors, proportional to, get rid of one of the exponentials, e to the, sorry, write it as k. The factor of tau cancels, which is good, and then e to the minus s bounce. So far this all seems standard. The crucial difference compared to what we did before lies in this prefactor, which is exactly the determinant of the fluctuations. So before we only had a zero mode, which we removed by integrating over the position of the instanton. Here we do again have a zero mode, which already actually in doing this calculation I've removed, and then that has effectively given me this factor of tau. However, in the case with two degenerate vacua, I argued that the instanton solution had no nodes in it. However, for this bounce solution, it's up there. If you look at the form of the zero mode, it's again given by something that looks like d by d tau, q bounce, it's a function of tau. Because all I'm doing is I'm taking my instanton and I'm shifting it slightly in imaginary time. However, this bounce solution now does have a node in it, so exactly because it's bouncing backwards, I get to some point and then I just stop and I move backwards. So the associated eigenfunction of the fluctuations has a node. Then our standard theorem tells us that this is not the lowest eigenvalue of delta, because we know the lowest eigenvalue of delta must have zero nodes. It's a bit tricky to prove exactly how many, so we have at least one negative eigenvalue. It's a bit tricky to prove that we actually do only have one negative eigenvalue, but at least in some limits that are analogous to the thin wall limit, that is true. So just assuming that is true and we have only a single negative eigenvalue, you see exactly that kappa becomes imaginary and the energy shift induced by this classical trajectory is imaginary, which is exactly what we wanted for a decay rate. One thing that is a bit tricky, in the end, I don't think it often matters that much for pheno because it only enters as some prefactor, which is usually not so well known anyway, is that if you want to extract the imaginary part of this prefactor, it turns out to be different to the absolute value of k by a factor of a half. For those of you who like complex analysis, in Coleman's book, there's a detailed analysis of exactly how you get out this factor of a half. You have to do something quite subtle where you have to continue the bounce solution in a way that means that it has no negative eigenvalues, then you analytically continue back, and this is what you get out. It's not super important in the end. The key thing is that with this imaginary energy shift, we have that the metastable vacuum will decay with a rate gamma, which is 2 times the imaginary part of k, e to the minus s bounce, which is equal to absolute value of k, e to the minus s bounce. And maybe just to make contact with what will happen in quantum field theory, once I've tunneled, or if I look at my bounce solution and now try to interpret what happens in real time, there's first of all going to be some imaginary time evolution that takes me to some point here, which is corresponding to where the bounce solution gets me to. This is happening in imaginary time because we know there's no classical trajectory in real time that can achieve this. But then once I get to this point, I somehow make the transition to real time, and then the subsequent evolution of the field will look like some, well, either quantum or to some approximation classical evolution starting from this point at which the field emerges. Actually, in this case, there's nothing analogous to friction in calculating the bounce solution, so the energy that the particle emerges with at this side will be exactly equal to the energy that it started with here, which is kind of plausible. And maybe to say this even more explicitly, if we want to know what the real-time evolution is immediately after the tunneling, then we start off our evolution with initial conditions, that is Q of some time, say T0, is equal to this tunneling point. Let me say, call it Q, I don't know, tilde, Q tilde. And Q dot of whatever time the particle emerges is equal to 0. Actually, these boundary conditions are exactly the same conditions of the particle on the bounce solution at the time when it turns back. And the equations of motion are just the analytic continuation of the Euclidean equations of motion back to real time. So this evolution, subsequent evolution in real time, is exactly the analytic continuation of the bounce solution back to real time. Okay, any questions on this? Nope. Let me then just say a few words about tunneling at finite temperature, which is what is actually probably more likely to be relevant to the real universe. So at finite temperature, one thing I can do is just tunnel quantum mechanically, but another possibility is I just wait around, I have thermal fluctuations, and eventually if the thermal fluctuations are large enough, they'll bounce me over the top of this potential without ever having to go into imaginary time. The field configuration, if you like, that I need to get to in order for such a, well, in quantum field theory, the field configuration, in quantum mechanics, the value of the coordinate q that the particle needs to get to in order to make some thermal transition to the other side is called a sphaleron. So if I say that the height of the barrier here, let me draw this a bit better, is given by the value at q maximum, then let me define the sphaleron this way, q maximum. And the rate of vacuum decay by thermal fluctuations is going to be just proportional to some Boltzmann action, Boltzmann suppression over T, where T is now the temperature of the system. Another possibility, once I put my particle at finite temperature, is I could have some thermal fluctuation partway up the barrier, and then from this point I could tunnel through. And indeed, you might imagine that if I've got some non-zero temperature, it's going to be easier to get at least some small fluctuation up and then tunnel, rather than tunneling directly across this, which you can see easily has a much larger, or potentially larger exponential suppression. Very schematically, a rough way to estimate what is the chance of this fluctuation and tunneling process is something like proportional to e to the minus energy of this fluctuation upwards, let me call it delta E, say, multiplied by e to the minus s bounce. Taking into account that now I'm starting from a position that is somewhat easier to tunnel from. Yeah, this gets slightly subtle because if you really want to understand how these sort of processes proceed, you're looking for fluctuations in real time and then switching to imaginary time. I think schematically, to identify what is the most likely process, I'm not sure if I would be comfortable completely just integrating over delta E, but you could see how this combination varies as a function of delta E, and then you could probably say that the most likely procedure is the one that minimizes this combination. And then there'll be some complicated prefactor that is probably hard to precisely determine, but that would at least, I think, give you a sensible analytic handle on how things will go forward. Yep, good. Any other questions? Okay, if not, then we can immediately move to vacuum decay and quantum field theory. And as always, the analysis is very similar to quantum mechanics, which is good. The only difference here is that now it would take infinite action for the entirety of space to transition at once. So a phase transition, or at least a first order phase transition, where there's some energy barrier between the two minima, will proceed by some nucleation of a bubble of the true vacuum, which then expands. In particular, what I expect to nucleate is a critical bubble, where the energy of this bubble, now thinking in real time, is equal to the energy of just having the false vacuum sat here with no bubble nucleated. The way that this happens is because I have some energy gain from being in the true vacuum at the core of the bubble, then some energy cost of the bubble wall. Just like in this case with the quantum mechanics, we exited the tunneling process with zero energy, or with the same energy that we started with. Here I'm nucleating a bubble that has the same total energy that I started with. Yep. Yep, it turns out that exactly the bounce action will automatically give me the critical bubble. So we need the rate of appearance of such bubbles. So again, we can make use of the Euclidean actions. So now this is ddx. Let me just put in delta mu nu to emphasize that this is Euclidean derivatives. D nu phi. Such that just like before, we have the energy is minus limit as tau tends to infinity, 1 over tau. So here we're taking the large tau limit, just like usual, to extract the lowest energy eigenvalue. So this means that our boundary conditions, in order to have finite action, have to be phi of x minus tau over 2 is equal to phi of x tau over 2. And let me suppose that, just to set up the conventions, let me imagine that I label this potential, this point, phi minus, point phi plus. Phi minus. Sorry, so let me write this way, just to be careful. Minus. We also need that the bounce is localized in space, as I say, in order to have finite actions. So phi of x tau this way, phi minus. Hopefully this looks very familiar from the cubal example, just with the difference that now we're working in 4 dimensions, 4 Euclidean dimensions, whereas in the cubal situation we're working in 3 dimensions. We want exactly a similar kind of, now in 4-dimensional bubble solution that is localized at some region. We have Q0 outside, or phi minus, I'm now calling it, some value inside that is going to be, depending on how the energy difference between the two vacua is set up, maybe somewhere near phi plus, or at least on the other side of this barrier inside. And then because we want finite action everywhere else outside, we have to be at phi minus as well. Okay, to find a classical solution to this Euclidean equation of motion, we make use of O4 symmetry. So let me write my now bounce solution in field space. Phi is equal to phi bounce as a function of r, where r is the Euclidean distance from the origin, so value of x squared plus tau squared. And the ordinary differential equation that I get out looks exactly like the cubal one, just with a different numerical factor here because I'm in a different number of dimensions. Prime of phi. And now because I've gone into these radial coordinates, I don't need to bounce forwards and backwards. All I need to do is start down here from tau is minus infinity. Well, in this direction, if I think starting from in this direction, I bounce. If I think starting from the origin of this object, which is most natural in terms of this r coordinate, I need to start at some point here and find a solution that as I go out from the center of this object, roll down here, and then eventually just stop at the point phi minus. Is it clear what I'm searching for here in this bounce solution? Okay, good. The existence of such a solution can, just like again in the cue ball situation, be argued for by some overshoot, undershoot argument. This friction tends to take away energy from the particle, so if I start down somewhere here in the valley, then I will never reach the top of this hilltop. On the other hand, since there is assumed to be some hilltop on this right-hand side, if I start sufficiently close to that, then simply I could just wait forever or wait as long as I want. This friction term dissipates away, and then it just reduces down to Newton's equations of motion with no friction. So at that point, I will definitely overshoot this lower hilltop here. Maybe it's interesting to ask what other possibilities I could have. For example, maybe over on this right-hand side, actually, I don't have a minimum, but I just continue going down forever. That would correspond to an inverted potential that looks something like this. And again, you can convince yourself that in this situation, I can always find a solution that stops at this hilltop, just making it. And then once you've carried out this calculation, you can easily get the bounce action SB. Then all that we have to do is carry out our path integral over fluctuations around this action, sum over all the different bubbles that can be in different locations, just like in the quantum mechanics example. Let me say, first of all, just for one single bounce, we have a factor of the volume coming from the different. Let me say, I'll remove the zero modes as usual, integrate over the possible positions of this instanton. This gives me a factor of the volume, space volume times the time, something that I'll call k, which I'll define in a second, then e to the minus s bounce, where k is proportional to now det prime minus del squared to the minus half, just like in the quantum mechanics example. And now I've put on this prime just to indicate that I've already removed the zero modes. Hopefully it's plausible, given the quantum mechanics example, that actually this determinant factor has a negative eigenvalue. Indeed, it turns out that it does. One way you can prove this is by doing some analysis actually similar to Derrick's theorem. It turns out that if I consider some deformed field profile, phi lambda, as a function of r, which is phi bounce under r, then actually the bounce solution is, okay, let me say unstable to this sort of rescaling for any lambda. If I make lambda slightly bigger than 1, I end up with a slightly smaller action. If I make lambda slightly smaller than 1, I also end up with a slightly smaller action. In particular, after a small amount of work, you can show that ds bounce by d lambda squared is something like minus 2 integral naught infinity 2 pi squared r cubed squared, which is less than 0. So now I have some fluctuation that definitely decreases the associated action and therefore corresponds to a negative eigenvalue. It's probably a bit, or maybe a bit harder to prove that this is the only negative eigenvalue, but it turns out that it is. And in this case, this k ends up imaginary. Correspondingly, let's say, the energy of the ground state picks up an imaginary part, and this and just like before, summing over all the different possible locations I can put this instanton we have, and summing over multiple instanton solutions, this delta E is proportional to minus V, this factor of kappa, e to the minus s bounce, which means that I now get a vacuum decay rate given by this expression where gamma is the decay rate per unit time. And maybe not surprisingly, this factor of volume turns out that the rate of nucleation of these critical bubbles is, well, what we actually care about is the rate per unit volume. Okay. All okay on this? Good. Okay. Let me maybe leave that up and just write. Here, this capital M is just something coming from like this complicated evaluation of the fluctuation determinant. If the typical mass scale in my theory is, or let me say that M is the typical mass scale in my theory, if you really wanted to do a precise calculation, you'd have to work quite a bit harder to really pin down what this factor is. As we'll see for cosmological phase transitions, usually actually it's the exponential that's the key thing. Sorry, that should be m to the 4. Again, just like in the cue ball case, we can make some analytic progress and get some understanding of what this bounce solution looks like in the limit where these two minima are close to degenerate. So in particular, let me suppose that v of phi minus v of phi plus is equal to epsilon. And let me suppose that this is small compared to, say, m to the 4. Here, this m just being schematically, say, the mass of excitations around either vacuum. Then, in order to have this critical bubble emerging, well, in order to find the bounce solution, I need to wait a long time near the second hilltop in order for the friction to dissipate. That corresponds to this critical bubble being very large, so that I get a large contribution, large negative energy contribution from the bulk, which is reasonable given that epsilon is small. So in order to have zero total energy, I better have a large volume to counteract the surface term. So now if I consider this starting off near phi plus on the interior, ending up at phi minus on the exterior, then when you go through the details of the calculations of the bounce action, we get minus epsilon pi squared over 2 r to the 4. And then sigma, where this is now the bubble wall tension, just like the domain wall tension we saw before. So to be completely explicit, sigma is integral between phi minus, phi plus, phi. Moreover, just like we saw for all of our topological defects, that these were solutions of the Euclidean equations of motion, and therefore in some sense were the lowest energy, or at least extrema, of the field configurations in a given topological class. Here we also should have that ds bounce by dr is equal to 0. And that in turn gives me an expression for r star. Let me say, call the size of a critical bubble r star. Which turns out to be 3 sigma over epsilon. And the corresponding bounce action is b to the 4. And maybe the only important thing to emphasize here is that as I make the energy difference between the two vacua smaller and smaller, the lifetime of the false vacuum increases to become arbitrarily long. This is not surprising. It means that when I get the energy difference very small, I need a larger and larger critical bubble to form, and the associated bounce action is increasingly large. Maybe a small question for you. So we saw already at the start, quantum mechanically, that tunneling between one vacuum and the other vacuum occurred at some finite rate, even when the vacua had degenerate energies. Why does this not occur here? So what is special about quantum field theory rather than quantum mechanics that means that I don't have tunneling between two vacua? Yeah, precisely right. So actually this is why we can have spontaneous symmetry breaking. It takes, because I would need to nucleate an arbitrarily large bubble, it would take infinite energy in quantum field theory because there's infinitely many degrees of freedom that would need to simultaneously tunnel. Yeah. Okay, so that hopefully seems completely sensible and plausible given what you've seen this week. Let's also see what it looks like from the real-time perspective. So just like in the quantum mechanics example, we saw that the particle suddenly appeared in real time from the real-time perspective, having tunneled in imaginary time. Here in real time, what we see is a critical bubble just appearing from quantum tunneling in imaginary time. As a sort of sanity check or consistency check, the energy of such a bubble is given by minus epsilon 4 pi by 3 r star cubed plus 4 pi r squared sigma. And unless I made an algebra mistake, hopefully if you put in this value of the critical bubble radius, this thing will identically vanish, which indeed is consistent with what we expect. As far as the real-time evolution is concerned, the initial conditions say that the bubble appears at t is equal to 0, function of x, are equal to the bounce solution evaluated at x, and let me say that the bounce occurs at tau is equal to 0, and we have the dt phi, slightly schematic notation, but it should be clear. It's d tau. So the bubble appears with whatever size it has, and it appears stationary. And then subsequently, at least in the limit where classical field theory is a good approximation, the bubble will just evolve classically. So follow the equations of motion. Del squared minus dt squared, let me put my minus signs here. Phi is equal to phi. Okay, next question for you. Let's suppose that this is happening actually in the real universe, and so there is some Minkowski space-time, say, an observer is sitting there and they just see a critical bubble appear, and then you can imagine that for an observer in a suitable reference frame, the bubble appears stationary, the bubble then expands, and everything is fine. However, we know that special relativity should work in our theory. So what does an observer who is boosted relative to the first observer see for this process? Do they see that the bubble is somehow deformed by the working in a different frame? Does the bubble expand in some way that is not spherical? And is this somehow, this tunneling process, picking out some preferred reference frame in our universe, which would be extremely weird? Does anyone know the answer to this one? Yeah, exactly. So the key point is that we need this to be Lorentz invariant, and actually all observers should see exactly the same process of a stationary bubble that then expands out at a speed that is independent of what reference frame you happen to work in. Yeah, very good. The way that you can see this happening is that actually the original bounce solution has O4 symmetry, and this descends when I do my analytic continuation to real time to O3,1 symmetry to be yes, I think so. I think the observer at that point would just, well, if the observer's properties depended on the value of phi, it would be probably somewhat traumatic for them. Maybe I can mention, I think I don't have time to talk about this, but there's an even more dramatic process called the bubble of nothing, where if I look at some particular theories with Kaluza-Klein reductions, suddenly, from the perspective of a real-time observer, space-time just disappears completely. So this is much, much worse than just the value of a scalar field changing. So very explicitly, if I analytically continue the bounce solution back to real time, my solution looks something like the bounce solution, but now evaluated at a radius x squared minus t squared. So if I think in the thin wall limit where there's a clearly defined edge to the bubble, then the position of the bubble wall as a function of real time becomes x wall squared is equal to r star, the critical radius squared, plus t squared. And this is now manifestly a Lorentz invariant expression if I put the t squared on that side. Another kind of interesting feature is that the bubble speed, at least in this idealized scenario where we have no friction, expands asymptotically, accelerating to the speed of light. So actually the energy of the bubble wall is, let me say, its radius, 4 pi position of the wall squared, its tension, and then 1 minus v squared to the minus half. Calculating the velocity from this expression, we get that this is given by 4 pi x wall cubed sigma over r star. And at least in the thin wall limit, this is given by, after a few small lines of algebra, 4/3 pi x wall cubed times the energy difference, which is kind of interesting because now we're seeing that actually, at least in this idealized scenario, all of the energy that is in the interior of the bubble being released, because we're now in the true vacuum, not in the false vacuum, is getting put into the energy of the bubble wall. Okay, good. Any questions on this so far? No. Let me give just maybe one slightly more non-standard application, which is a breaking of a metastable string, as I already mentioned in the lectures on solitons. So here we could think of, say, a string breaking by nucleating a monopole-anti-monopole pair. In real time, this would correspond to my string being here, and then suddenly I see that there's a monopole nucleated here, anti-monopole nucleated here, and the string can then break. Let me say that the monopole mass, I'll call it mm, and the string tension I'll call mu. Then, provided we're in a situation where the string tension is much less than the monopole mass squared, we can think of this as being some quantum tunneling process. The only difference to the vacuum tunneling that we talked about just now is that this tunneling is happening on the string world sheet rather than on some four-dimensional Euclidean spacetime. So now what the bounce action will look like in imaginary time but on the string world sheet is a pair of monopole antimonopoles appearing, going through some bounce and then returning and annihilating, which when we then switch back to real time will look exactly like this process, with the subsequent analytic continuation of the bounce action being these monopoles getting accelerated down the string, which is analogous to the bubble expanding out in vacuum decay. So at least in something like the thin wall limit, we can estimate the bounce action here. If I say that the analog of the critical bubble radius is this distance r here, then the only difference is that now the number of dimensions change, so the various numerical factors change. But we get some thing that looks like this, which is effectively coming from the energy cost on the exterior of this circle, then pi r squared mu, which, if you like, is the energy gain from the interior where I no longer have a string. If I minimize this with respect to the radius, I end up getting that the rate of string breaking per unit length of string is now given by, again, some numerical factor, which will probably just be some typical mass scale in the problem to appropriate powers, and then e to the minus pi times mass of the monopole squared over the string tension, which is hopefully what I told you in one of the previous lectures. So there are cosmological scenarios where I could imagine that this sort of vacuum decay by tunneling would be relevant. Maybe the easiest way you could think of this happening is, suppose that I have some hidden sector that is extremely weakly coupled to the standard model and is never reheated after inflation. Then it could be at approximately zero temperature, and it could be that indeed the zero temperature calculation of vacuum decay is appropriate and gives us a good estimate of this hidden sector's lifetime. On the other hand, perhaps more plausible is that a phase transition would take place in the early universe at finite temperature. This could be in the standard model if I take some extension of the electroweak theory that leads, with additional scalars, say, that leads to a first order phase transition rather than a crossover. It could be by some additional dynamics at higher energy scales and so on. But either case, even could be in some hidden sector that is also reheated to some sizable temperature. But either way, what you should be actually calculating is the finite temperature decay. So just like in the quantum mechanics example, such a finite temperature decay can occur by just some fluctuation in the energy density due to this non-zero thermal bath that happens to create a critical bubble in some region of space that would then be able to expand. Let me maybe just schematically see, and again, just like in the quantum mechanics case, you can also get more complicated effects where I have some thermal fluctuation that gets me partway to tunneling to a critical bubble, and then with tunneling doing the rest. Let me just maybe very schematically show how such a calculation could proceed. So as you hopefully know, if I want to do thermal field theory, this corresponds to going to Euclidean time and compactifying the time direction. In particular, if I want to calculate the partition function, let me call it Z, of some quantum field theory at finite temperature, this is given by trace e to the minus beta Hamiltonian, where beta is 1 over t, which is given by a path integral d phi e to the minus integral from 0 to beta t tau, then the Euclidean action. The key distinction to what we've been doing so far is that the boundary conditions on this path integral are because of this trace that we require phi of x0 is equal to phi of x beta, with beta being finite and just set by whatever temperature we want to put our quantum field theory at. We can also almost by definition write our partition function in terms of the free energy and the volume and the temperature of the system, which then, due to this expression in terms of a path integral, gives us that this is given by integral minus infinity to infinity. And now it's convenient to separate out the zero mode of the field phi. Let me call that phi bar from the rest of the path integral. Let me call that as a path integral over d phi prime. To emphasize, this is removing the zero momentum mode from the path integral. Then e to the minus s Euclidean evaluated on phi is equal to phi bar plus phi prime. Now, all of this stuff, the integral over the path integral over the phi primes without the zero mode, is exactly what actually is called the thermal effective potential. So this we can say is by definition integral d phi prime minus infinity infinity If this isn't too familiar, it's not too important, or I won't try to cover it in complete detail. All I'll say is that this finite temperature effective potential is exactly the same object that we talked about earlier when we were talking about symmetry restoration at finite temperature, and a zero temperature potential that looks like this going to some finite temperature potential that looked like this as a result of thermal fluctuations. Looking at that expression and that expression, we can see that in the thermodynamic limit of space volume going to infinity, we have that the free energy of the system at a temperature T is equal to the thermal potential evaluated at its minimum. Okay. So let me now assume that indeed the way that the effective potential evolves as temperature decreases in the universe is such that there is a first order phase transition. And maybe let me just write one more expression here that from our starting path integral, we also have that the free energy density, let me say, is equal to minus T. Let me just write it as Here, the only difference between capital F and lowercase f is some factors of volume. I won't try to be too careful with those. In the end, we'll always get the thing out that we wanted. A reasonable guess, which I think actually hasn't been proven, and indeed there might be important deviations away from this, is that our expression that the decay rate at zero temperature, being -2 times the imaginary part of the energy, may well plausibly go to, at finite temperature, gamma is equal to -2 imaginary part of the free energy, where the free energy is evaluated with this kind of expression here. So how do we calculate this, assuming that we have again some potential that has a barrier between the two minima? Well, we take our path integral, which is given our expression for the free energy, and we calculate the semi-classical contributions to, well, effectively tunneling that allow a nucleation of bubble of the true vacuum. So, just like before, we need a solution of the Euclidean equations of motion. Let me call it phi bounce again, which is equal to 0, with the property that phi bounce of x 0 is equal to bounce beta, because we have that all the contributions to the path integral are periodic in imaginary time. And we also need that at spatial infinity, if we're going to have finite action, we better have that limiter's absolute value of spatial coordinate goes to infinity. Phi bounce x tau has to go to the false vacuum. Let me call this again phi minus, phi plus. There is, however, one crucial difference that we get as a result of going to finite temperature. So if you remember, in the vacuum or zero temperature case, we had to take the large, I called it curly tau limit, in order to extract the lowest lying energy eigenvalue in our matching up between the path integral and our sum over eigenvalues. In this case, we don't need to take an analogous limit because we have that beta is finite. It's just set by whatever temperature we put our system at. So it might be that if we put our system at low temperature, beta is extremely large, but we could also imagine that our system is at a high temperature, in which case beta is very small. As a result, in order to get a finite action solution of the classical equations of motion, we do not need that this is equal to phi minus. What this means is that whereas in imaginary time at zero temperature, if I think of this as being imaginary time in this direction, I needed at the far distant past and the far distant future to be in the metastable vacuum, just with some localized bubble here. Now, because we keep beta finite, so that is getting stretched infinitely far in this direction, this distance is finite and is just set by beta, so I don't necessarily have to have this being phi minus. In the limit when the temperature of the universe is very small, then actually I am close to this situation and the extent in the vertical direction is very large compared to the size of the O4 bubble that we obtained in the zero temperature calculation. So let me write this as T is approximately equal to 0. So given the large extent in the vertical direction, the solution for the critical bubble will be very close to the O4 bubble that we already obtained. And just like before, we sum over bubbles with appearing in all different places, and we'll get out a vacuum decay rate that is extremely close to the zero temperature result. On the other hand, when we go to temperatures much larger than 0, here I'm being a bit schematic, of course, I should say, compared to any mass scale in the problem, the vertical axis gets extremely squeezed, and in particular becomes much smaller than the size of the critical O4 bubble. Then what happens is that actually my bounce solution no longer has O4 symmetry because I've cut off the vertical direction, and what I get out is O3 symmetry. So I still have symmetry in the space directions coming out of the board and horizontally, but I no longer have my full O4 symmetry. In this case, the Euclidean action associated to the bounce is just given by beta from the integral over the imaginary time direction. So that's 1 over t. And then times the action in the space directions. 3. That's 1 over temperature. Bounce 3. Where now the three-dimensional bounce action satisfies something that looks like d squared phi by r squared is equal to again, much like before, just with some numbers changed because the number of dimensions has changed. And maybe skipping to the important punchline, at sufficiently high temperatures, the decay rate per unit volume will scale as a e to the minus s bounce over t, with this 1 over t coming from this integral over the imaginary time direction. And again, you can calculate this, let me call this s bounce, comma 3, this just by solving these classical equations of motion. And again, this prefactor will be some mass scale of the problem coming from some combination of the fluctuation determinant and other stuff. But very parametrically, you might expect it to be something like temperature to the power of 4. Yep. Yep. Yep, absolutely, this is true. But is not too worrying because now we have some thermal bath which picks out a preferred rest frame, so I don't worry about losing this. Yeah, but yeah, good point. Okay, maybe very briefly at the end, I will just try to convince you that actually there are observational reasons that one might care about this. There's a lot more I could tell you about friction on these bubble walls, especially in the finite temperature case. So in this case, once the bubble is nucleated, it's going to expand outwards, passing through some thermal medium. The scattering of the bubble wall with this bath of particles will affect its evolution pretty dramatically. If the friction is sufficiently weak, the bubble wall can still accelerate arbitrarily close to the speed of light, and potentially at this point it would carry a large fraction of the vacuum energy, just like in the zero temperature case. On the other hand, if I have a substantial amount of friction, then actually the bubble wall will just accelerate to some very subspeed of light velocity, and then all energy released after this will go into the plasma of the particles somehow in some shell just behind the bubble wall, or even in some cases just in front of the bubble wall. And this can change the dynamics really quite dramatically. Yep. To go back to real time, I think that is probably very hard. Indeed, actually, this identification, this goes to this, is slightly dodgy because there's no clear way to actually interpret what is happening in real time. Probably, if you really wanted to do this from scratch consistently, you'd have to actually work in real time the entire time. So I think this is not really, yeah. But that would in practice need some classical field theory simulation at finite temperature with fluctuations. So let me just very briefly try to convince you that you should potentially care about a phase transition happening at the 10 TeV scale or the 100 TeV scale, which given that, well, given timescales for building a collider, are potentially going to be very hard to probe directly with particle colliders. Now, you've probably seen in one form or another that gravitational waves in the early universe follow an equation of motion that looks something like this. So let me call that H double dot rather than H tilde, Hij. Here I'm working in Fourier space, and I've expanded my metric as ds squared is equal to minus dt squared plus j xi dxj. So here on the right-hand side, just like we were talking about with cosmic strings, the gravitational waves are being sourced by the stress energy tensor. If I want to be more precise, this is being sourced by the part of the stress energy tensor in order to get transverse traceless parts. But for our purposes, let's just say that this is and let me say that the phase transition happens on some time scale. Let me say b, which is roughly 1 over the Hubble time. So if I imagine that my universe is cooling down, as I go to lower temperatures, this rate is going to get exponentially fast, and I might think that over a Hubble time in which the temperature of the universe decreases by an order 1 amount, this exponential, this thing that we're taking the exponential of, will increase quite substantially. So once we take into account the exponential dependence, once I start nucleating critical bubbles, I would guess that everything will happen within 1 Hubble time. Indeed, this turns out to be the case in semi-realistic models, let's say. So given that we're sourcing our gravitational waves this way, over this kind of time scale, I would expect that I would get some expression like h dot is 8 pi g stress energy tensor over b. Have I got the... Yep, so I'm just taking h double dot, multiplying it by a typical time scale. So this is what I expect for h dot. And at least with this normalization of the metric, we have that the energy density in gravitational waves is roughly equal to h dot squared over 8 pi g Newton, which then gives me a somewhat plausible estimate that the energy density in gravitational waves is 8 pi g, with this factor coming from that. The stress energy tensor squared divided by b squared. Okay. So let me say that B is equal to Hubble. This means that the energy density in gravitational waves over rho total is roughly equal to g newtons. So let me say total. Put a factor of rho total in there. Okay, and then 1 over b squared, which is approximately equal to, unless I got some definition of b upside down, schematically the Hubble parameter at the time of the phase transition divided by b squared times this. And yes. Sorry, I think I want that. Yeah, thank you. That's better. Okay, that way up now works. That's dimensionally correct. And probably here I want b times h star. Okay, then stress energy divided by rho total squared. Okay, good. All this to say that if the phase transition proceeds on a timescale of order a Hubble time, if the stress energy tensor corresponds to something that has entries that are roughly comparable, ignoring things like which particular indices I'm extracting, to the total energy density in the universe, which indeed would be the case if I have the difference between the two vacua here. Epsilon is roughly comparable to difference in energy density. Epsilon is roughly comparable to rho total. And if I manage to transfer all of this energy efficiently to either the bubble walls or to some plasma surrounding the bubbles, then I can get an order 1 fraction, maybe not too far off order 1 fraction of the total energy density of the universe being transferred into gravitational waves at this time. That means that redshifting to the present day, we potentially have something like omega gravitational waves today would be just like in the case of calculation of gravitational waves from cosmic strings. Putting in factors of temperature, we get something like omega radiation, because the gravitational waves once produced redshift like radiation. And then let me say b times h star squared, and schematically pi ij over rho total squared. And the frequencies of these gravitational waves will typically be pretty similar to at the time of their production, will be not too different to the size of the Hubble parameter, which corresponds to frequencies today 10 to the minus 5. And let me say, just picking out the key factors, the temperature of the phase transition divided by 100 GeV. Now, if you take somewhat realistic values for this ratio, say coming from numerical simulations, maybe it's a bit smaller than 1, but you can see that actually this being 10 to the minus 4, 10 to the minus 5, something like that, actually a phase transition is potentially reasonably observable in upcoming gravitational wave detectors. We'd need something beyond the standard model in order to create such a first order phase transition, but if it does occur, we can potentially have some hope of detecting it. Of course, I've skipped over many details, probably not least how to actually calculate these reliably, how to take into account friction and so on. But it's a direction where there is hope of discovering new physics beyond the TeV scale. Okay, I think that's all I want to say, so thanks.